relativistic particle. So just to remind ourselves, let me start by writing them down. The primary expression which we had was x2, x1, which we expressed as an integral, which was minus I upon 16 pi square. You should compare with your notes and if there is error in pi factors or something. Some d mu upon mu square e to the minus I mu. We wrote it as m square minus I epsilon. We will come back to this. Then we had the term coming from the propagator, which was I x square, which is x2 minus x1 the whole square upon 4. This was our primary expression. And then we did its Fourier transform. So first we did the Fourier transform just in spatial coordinates. So we computed x2, x1. And we did the spatial Fourier transform of this, which was e to the minus I p dot x d3x. And we found that this has a remarkably simple expression, simple but disturbing expression, omega p e to the minus I omega p modulus of t. Just to remind you, if you have done this with non-relativistic particle kernel, we would have had this 1 upon omega to 1 upon 2 omega p. Instead, we would have had a theta function here, and we would not have had this modulus of t. And the modulus of t tells you that the positive frequency modes are being propagated forward in time, negative frequency modes are being propagated backward in time, which is what I said was disturbing. Second was, we said that any propagator, if it has to be transitive, then you cannot have a constant in front. It must have a form e to the minus I omega p times t. So even for t greater than 0, when positive frequency modes are being propagated forward in time, transitivity goes for a tops because of this extra factor. Okay. Then we did one more expression, which was to compute the 4-dimensional Fourier transform, which was x2, x1, e to the, okay, now our notation it will be IPX here, so that the spatial minus sign is picked up, d4x. And this again we found has a remarkably simple form. It was I divided by p square minus m square plus I epsilon. This I epsilon came about because we had put an I epsilon here, and this is the expression which we have. And I told you that this is what is known as the Feynman propagator in Fourier space, and this is what we will be using in quantum field theory repeatedly. And here we are just getting it out. Okay. Now I want to begin by discussing several interrelated properties of this and connect them up and all that before we go further. This I had already discussed to some extent, but we will look at it in a little bit more detail. In particular, I wanted to talk about the non-relativistic limit, which many people asked questions while we were going on. So let us finish that off here. So if you look at this expression, this is the easiest expression to get a non-relativistic limit. So if I am going to take c going to infinity limit, what will happen is this? So let us look at it. So you take the Fourier transform and let us take the c going to infinity limit of the Fourier transform. I only have to get the non-relativistic limit in the Fourier space. Because for e to the I p dot x is one quantity which doesn't change between relativity and non-relativity in the non-relativistic limit. So that is fine. So let us look at this also. So I have an expression like 1 upon 2 omega p. If we expand it out, it is theta of t e to the minus I omega pt, which we all love. And then you have a backward propagation in time which is a purely relativistic feature, omega p. This is what we have. Okay. Now, when you in this, we know that this omega p stands for p square plus m square, spatial p square plus m square raised to half. So in the non-relativistic limit, remember that this is p square c square and m square c to the power 4. So in the non-relativistic limit, the energies are going to be dominated by the rest energy m. So you pull that m out, then you get this m square on the denominator, and you get a half. Then, okay, when you multiply it again by that m, it picks up p square by 2m. Okay, so this is fine. So omega p has a mc square response energy plus the kinetic energy. So in this denominator, you just put 2m. So there is an overall factor of 1 upon 2m in the propagator. This is because if you remember, we had a c into 2m when we calculated the quantity. And I said that people like to have a particular dimension for relativistic propagators. So we will set c into 2m equals 1. This is just to match with the other paper. So that is where this 1 upon 2m comes from. So let us not worry about that. Then let us look at this also. So here e to the minus I omega pt is going to pick up a e to the minus I mc square t from this m. Then you get a p square by 2m term, which is fine. Therefore, you go back to this and you express that quantity as 1 upon 2m, which we don't care. Then you take that e to the minus I omega pt out. So you get e to the minus I, let me put c's for a minute. This is the leading term in that. Then you get theta of t e to the minus I p square t by 2m. This comes from the second term here. And I have taken this out. So in the second term I get theta of minus t, a term which will have e to the plus, there is a plus 2mc square t times various things. We don't care about that. The way one argues for non-relativistic limit is to say that, well, there is a theta of minus t here which is extraordinarily disturbing, we don't want it. But it is multiplied by e to the 2mc square t, and we are taking c going to infinity limit. So the phase is oscillating very, very rapidly. Therefore, we will say that this term is not going to contribute in that. That gives you theta of t. This is an extra phase. This entire thing is a relic from the relativity, an extra phase. And this is just your standard non-relativistic current. Okay? This is how the non-relativist limit is obtained. Now, if you recall, I told you that this has nothing to do with relativity or quantum mechanics. This happens in optics. So, in the paraxial optics limit, when you start from an electromagnetic field equation which is second order in time, where you will never be able to make light go only in one direction. In paraxial optics approximation, we just take the forward direction as one, let's say plus z. When we discussed it, that slit and screen experiment, I said that let us just look at the forward direction to be plus z, and the backward direction we just suppress it. And we suppress it for reasons which are very similar to this. Okay? So this is why in this limit, transitivity is recovered, because this is just an overall constant which will scale up. Then you have just theta of t e to the minus I t square by 2ft. The moment transitivity is recovered, you know that the wave function at a later time can be determined entirely in terms of wave function at a given time, which means the equations of motion has to be first order in time. Right? So this is precisely what we do in paraxial optics. The equations of motion are second order in z coordinate. So it will allow it to propagate both in positive z direction and negative z direction. But when you have a slit with a hole and a screen, you are going to suppress the backward propagation in the z and pick up the forward propagation. So that part I hope is clear. So that is how we get the non-relativistic limit. Okay. We will revisit it after we have got particle interpretation from field theory, etc. etc.
Sir?
Yes.
In this particular step,
Yeah.
So taking e raised to minus I c squared t out.
I could have taken the other one out.
So then what?
If I had taken the other one out, I thought somebody would ask that. Then you would have, what you would have called particles, I would have called antiparticles. And it would always go backward in time, and with one time reversal, I could have got it. Okay? So it really doesn't make much sense. It looks very disturbing, but it is not. As long as I retain one of them and kill the other, it doesn't matter. But it is more of a convention as to which one you want to read. Okay? It is like saying that in paraxial optics I have a screen and a hole. I'm going to think of light propagating in this direction, then I want to suppress this. I could have equally well talked about light propagating in this direction. As long as I don't keep both of them and have an interference between them, there is no problem. Okay, fine. Good question. Okay, now let us go a bit further. And I want to look at the interrelationship between this and this. Okay? Some of this I threw in as an assignment in the last week, which I am sure none of you have looked at. Oh, you are nodding your head, so you people have looked at it. Okay. So there are these boundary conditions which I wanted to discuss a little bit. Okay. So what are we going to do? I want to do an inverse Fourier transform on this and get this. Okay. So that of course is trivial, because if I had this relation, I could have also written it as x2 x1 equals integral d4p upon 2 pi to the power 4 I p to the minus ipx now divided by p square minus m square plus ix. Okay. What is this? So let us try to do this integral. Okay. We know what we should get, but let us do this integral for a particular purpose. I keep the d3p as it is. So there is a d3p over 2 pi divided to and in this px is p naught x naught minus p dot x. So I retain that e to the I p dot x out. This part is fine. Then I am just going to do a p naught integral. So that is minus infinity to plus infinity d p naught divided by 2 pi, and I have here the e I times e to the minus I p naught t divided by, I am doing a p naught integral, so let me expand the p naught part of that. So there is a p naught square p naught square, p square is being expanded, the 4-dimensional square of a 4 vector. So it is p naught square minus mod p square. That minus mod p square I am going to combine with m square and write it as omega p square. So I write this as omega p square plus IH. This is what we have. Okay. So I want to do this integral first. Alright. Now what should I get? What remains is this d3px integral, which is exactly what we have done here. So this integral should give you an answer which is 1 upon 2 omega p e to the minus omega p modulus of p. So I will leave it you to work it out. But there are a few important points which I want to stress. This is a p naught integration along the real line. Assume for a minute I had not put this I epsilon. When we did the integrals, we only had this m square. Then I said that, look, I want the things to converge properly at upper limit. Then I said, let me put I need a minus I epsilon, so that the minus and minus will go away, and I will give me a minus epsilon, so that it converges at the upper limit. So it was sort of very innocuously introduced. But if that I epsilon was not put there, then I would not have had this I epsilon here. Then when I do the integral along the real line, so this is p naught, real of p naught, and this is the imaginary part of P naught in the complex P naught plane. When I do the integral, I am doing it along this real line, and I will have poles at omega p and at minus omega. So this integral is not well defined. I mean, it doesn't exist. Okay. The moment I put the I epsilon, it tells us where how to do that, because now the poles are at P naught is equal to square root of this quantity. Okay, so where are the poles now? Let us do that. Since the only time we are going to do this. Omega p square plus I epsilon raised to half. Okay, so what happens here is you pull this omega p out, taking the positive square root. Then you have again and 1 plus I epsilon here. That is magic of the epsilons, because if I pull omega p square there, this is epsilon upon omega p square, that is again an epsilon. As long as you don't flip sign, it is fine. So omega p square is positive, it is another epsilon. Then the square root becomes, because epsilon is small, half times that, so it is again epsilon. So this is what we have. Okay? But the overall, I should have picked a plus or minus here. So it tells you that on the positive omega p, it is at omega p plus I epsilon, and in the negative omega p, it is at the other end. So what it tells you essentially is that instead of doing this integral here, I should have done the integral along this. Let me draw this a bit more clearly here. One more diagram. I could have done an integral which goes like this, which is how most of the other books would probably give it. So there are two poles here. I avoid one pole by going around like this, and the other pole you avoid by going around this, which is equivalent to, instead of working along this real P naught, you have tilted it slightly. Now of course the function is entirely analytic in this part, which means if I can do this, I can do this. I can work along the Euclidean or the imaginary direction. Remember long back when we did the time integrations, I pointed out that there is this continuation to the Euclidean time. When we went to the Euclidean time, as far as time integrations are concerned, we rotated like this. The t here was mapped to t here. Here we have to rotate like this. And it's just the way p naught t term combines together. So the rule for integration is that you avoid the poles in this following way. That is, you think of your P naught as P naught into e to the I theta, where theta you can either think of as an infinitesimal. This is your angle theta. The two most convenient thetas are one which is infinitesimal, when it just leaves it by this I epsilon. The other is theta is equal to pi by 2 when you work along the imaginary direction. So let us take a look at that imaginary direction integration a little bit, because that we will use in field theory quite often.
Sir,
Yeah.
slightly confused. So P0 square is omega p square minus n epsilon, right? So
P0 square is omega p square. Yeah, that's correct.
So for positive omega p, it's
No, if you take the square root, you will get this. Maybe I wrote it wrongly. Is that what you're saying? Yeah, maybe I wrote it as plus I epsilon. So,
yeah.
okay, let us work this out. I mean, so this gives you P naught equals omega p square. Yeah, I probably wrote it wrongly. Minus I epsilon square root. So this will become 1 minus I epsilon. Right? With a plus or minus sign. So when I take omega p is equal to plus, the minus I epsilon tells you that that pole has to be pushed below the real axis. Either I can push this thing below the real axis, or I can take the contour above. And exactly the opposite here. Yeah, okay, I wrote it wrongly, but since I know what the contour was, I drew the line correctly. Okay, so this is correct. Now in the exercise I have given you two more examples. One was that instead of putting omega p square having an imaginary part, I could have written there, I could have thrown the imaginary part inside this omega p. That is, I could have replaced omega p by omega p plus I epsilon or omega p minus I epsilon. If I had done that, I would have avoided both the poles by pushing them below or both the poles above. That would mean that when you close the contour, one of the contours, either on the top or on the bottom, will give you 0. Okay? So when those kind of propagators, so to speak, will vanish either for t greater than 0 or t less than 0. These are called retarded and advanced propagators, which is very useful in normal physics, but in quantum field theory what we need is this straight object, where both the poles contribute. One contributes for positivity and the other contributes for negativity, which is what we want to finally end up getting. So you should do this integral and convince yourself that you do get this, which you will, because it is it should be fairly obvious from here, because once you have up to this point, you close the contour depending on the sign of t. If t is positive, you close in one direction, and if t is negative, you close in the other hemisphere or semicircle, and as a result of which you are going to pick up two different contributions, and that will give you the modulus of t. Okay, fine. So you are this. Yeah.
Has it got something to do with causal and anti-causal effect?
Not at this stage. Now, there is a lot of books which will try to talk about this as in terms of causal and anti-causal and things like that. What is meant is that if you have a retarded propagator, suppose you have a retarded propagator on t minus t prime, that will vanish for t less than t prime. So when you are using it as a Green's function for a differential equation, and if there is a source, you say that if the source does something at time t, its effect will be felt only at t greater than that time at which it does, at t is equal to 0 if it does something, only at positive t the effect will be felt. So you call it causal. And similarly, if I use an advanced propagator, then it will be called anti-causal. But these are really not applicable in the field theory context. Okay, so I don't want to even bring it in. See, the philosophy always has been that you start with the action for a relativistic particle and you find your propagator, which we have done. So this propagator for us is sacred. When you write it in Fourier transform, whatever you get there, you pick it up. Now that Fourier transform happens to have this modulus of t, which tells you that certain modes are propagated forward in time, certain modes are propagated backward in time. Since we finally want a causal description in terms of fields, which we will introduce, at that time you can talk in terms of what kind of propagator it is and what it is propagating. Okay? But it is not very useful at this stage. So we will just think of this as the momentum representation of the Feynman propagator. Okay? And you will have this. Okay. So the when you evaluate this, you will get this result. But I wanted to spend a little bit of time on this Euclidean continuation, which we are talking about. What are we doing here? Normally, when you look at the phases of quantities, you will have something like, let us say, P naught t minus P dot x. The thing which you would have normally thought that if I go to the Euclidean sector, in the Euclidean sector the signature is plus, 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 plus. So this should have become something in Euclidean with a plus sign. So if you do it naively, you will find there is a little bit of a problem there, and this can be confusing. So let me spend a little bit of time there. What we are going to do is that if you take a P naught here, that is going to be replaced by the P naught when it rotates. P naught will be replaced by I times P naught Euclidean, right? So that is how the rotation goes. So you get this, P naught will get replaced by I P naught Euclidean. T P naught gets replaced by minus I T Euclidean. We did this long back. Nothing happens to these, so they remain minus P dot x. So what you find is, there is a minus sign, I into I gives you a minus sign, they just go away. This becomes P naught in the Euclidean sector, T in the Euclidean sector, with a minus sign p dot x. Though you would have expected a plus x. Well, it is just a factor of life. It doesn't become plus. Okay. However, most of the time the integrals will work out as it should. So let me just show you that. Suppose you have an integral. What you will often have are integrals of the following kind. Just let us look at this kind of an integral which we have written down here. You will have an integral d4p, some function of p square, which is what is here, times some, let us say, e to the minus ipx in 4 dimension. And let us ask what happens to this. There is a p naught hiding inside this that will get replaced by I times p naught. So this integral will go into I times integral d4p in the Euclidean space. This p square is p naught square minus modulus of p square. P naught square, because of that I factor, will become minus p naught square. So this is going to go into f of minus p Euclidean square. Nothing happens with this. X, so to speak. Okay? You are with me up to this point. Now what we do is, we change the vectorial p to minus p. If I change vectorial p to minus p, nothing happens in the integration method. The limits will take care of it. Nothing happens here because it depends only on p square. In this will change into plus. Correct? So actually I should have written here the expression as p naught of e, t of e minus p dot x, which is equal to I integral d4 of the Euclidean p f of minus p square e to the minus I. Now it is p e x e with this sign being flipped. So this is what you would have normally written down, because you would have said that in Euclidean space all the signatures are positive. So I should have got p naught e dE plus p dot x, that is what is going to be here, and everything. So it works because most of the time we will be working with functions which depends only on p square. So you could have done that and you wouldn't go wrong, but this is the way it comes up. Another mistake which sometimes people commit is to forget this I. It is not that when you go to the Euclidean space, Fourier transforms becomes Laplace transform. They don't. I mean, I can have a 3-dimensional line Euclidean space, and when you do Fourier transform, you do e to the I p dot x. Okay? So in the same way, in the 4-dimensional Euclidean space, the Fourier transform, nothing happens to it. It is a Fourier transform of this one. Okay. So just as an example, what happens to this integral here, which we have? You pick up an I, and that I multiplies this I and gives you a minus sign. Then here this becomes minus p e square. So those two minus signs go away, and that integral will become integral d4 of p e upon 2 pi to the power 4 e to the minus I p e x e, nothing happens to Fourier transforms, divided by, in the denominator you have p e square plus m square, and there is no need for any I epsilons anymore. So this is something which you should spend a moment and understand. We have introduced this I epsilon prescription even in path integrals, and at that time I told you that most of the time the I epsilon prescription is completely equivalent to the Euclidean time prescription. So this is a demonstration in a simple context. Suppose instead of throwing in this I epsilon etc., we had started with this integral and said that I will regularize this integral, give it meaning by going to the Euclidean space. What would I have done? There is no I epsilon. Mu I know is like a time coordinate, right? So this I mu would have become some mu Euclidean with an m square. That is nice. This I d mu would have become just mu. This will pick up an I sign and that minus sign will go away. So I'll have 1 upon 16 pi square integral over a Euclidean variable and everything is fine here. What happens here? Here this mu, I want to have an I mu, so I put an I here and an I there. So the sign becomes plus. This becomes the Euclidean. For a moment it looks threateningly with a positive exponential, except that this x square here is t square minus mod x square. That becomes minus t square minus mod x square. So that sign saves you. So this entire integral has a very well defined limit in the Euclidean sector. So this would have gone to just to 1 upon 16 pi square integral 0 to infinity d mu Euclidean upon mu Euclidean square e to the minus mu Euclidean m square minus x square Euclidean upon 2 mu Euclidean. Everything is well done. Okay? So you should try as an exercise starting from here and doing all the Fourier transforms and asking what the Euclidean momentum representation of this propagator is, and you will get the solution. Okay. So if you are doing things in Euclidean, you don't need the epsilon prescription. It also tells you that the Euclidean prescription selects one propagator out of at least 3, which I have talked about: the advanced, retarded, and the Feynman. So in this particular expression, as I said, I could have put omega p plus or minus I epsilon, that would have given me advanced and retarded, or I could have put an I epsilon outside. Euclidean prescription picks out this particular I epsilon prescription, which is what we have seen. Okay, fine. Alright, so that is essentially all that I wanted to say about this. Now we wanted to ask the same question we asked for the non-relativistic propagator, namely, is there a Hamiltonian description for the whole field? See, the idea was that in the non-relativistic case, I wrote down a propagator and I could have thought of that propagator as an expression which arises by doing, this is in the non-relativistic theory, x2 e to the minus it times a Hamiltonian for the non-relativistic particle x1. So we introduced eigengets for the position and we worked this out, and we had a equivalence between this and the path integral expression. Now the question is, can I do it in relativity? Now I had already told you that you cannot do it in relativity. It should not work. Mainly because in a single particle description with localized position eigenstates will not exist in relativity. All kinds of things will go wrong. So I want to show to you where all these things go wrong. Okay? So let us try to repeat exactly what we did last time. We will start with a set of momentum eigenstates, and we will first write down the completeness condition for the momentum eigenstates. So we have something like d3p upon 2 pi the whole cube. Just recall what we did in the non-relativistic case. In the non-relativistic case, this is what we wrote. This we said was 1. Right? This was our beginning. Now in the relativistic case, we would like everything to be Lorentz invariant. So this part is not a problem. We are going to define this sketch to be Lorentz invariant objects. But this integral is a problem. But we know how to solve this. We found that the proper measure which we need to use in relativistic case is this with a 1 upon 2 omega p. This is a Lorentz invariant integration measure. So this with p will be the Lorentz invariant description of the momentum items. Again, recall that what I told you earlier on, preparing you for this, that in the non-relativistic physics you could either use position eigengets or momentum eigengets. Both are good eigengets for you. In the relativistic theory, the momentum eigengets continue to be a good eigengets. You can start with a particle with a given momentum, collide it with another particle with another momentum. But you cannot talk in terms of a particle localized at one point. Okay, that is what I am going to lead you up to. So you start with this. This is a very natural thing. Now what I am going to do is to hit on both sides by another ket with P prime. Okay. So if I put a P prime here, I get on the right hand side P prime. This has to hold. This means I can identify what this is. This requires P prime to be equal to 2 pi the whole cube 2 omega p, this is the new thing, derived as a function of p minus p prime. So now if you plug it in, this will get cancelled, and you integrate this p with a derived Laplace function, you recover p prime. Okay? This is the new feature, but this should not surprise you, because you want a Lorentz invariant normalization on the right hand side. This is the orthonormality condition for that. It has to be Lorentz invariant. The derived Laplace function by itself is not Lorentz invariant. You need to have this. That you can see by writing down this relation. See, integral d3p for us with a derived Laplace function on p minus p prime by definition is going to be 1. Right? So if I put here upon 2 pi the whole cube and 1 upon 2 omega p, I have to multiply on top by exactly like 2 pi the whole cube and 2 omega p. This again continues to be 1 because I haven't changed anything. So this d3p with this omega 2 over 2 pi and this is my Lorentz invariant normalization. This much is Lorentz invariant. Therefore, this with this should be Lorentz invariant. So the right hand side is Lorentz invariant, even though it may not look like it, but actually it does, because this is like 1 upon L cubed and this is the energy, and so it should be Lorentz invariant. Okay, so this is the first thing you do. Now what you want to do is to look at the translation of this into the X space. Okay? So what will you have? You would have written down, now there are different ways of arriving at that. One way of looking at this would be to think of this integral with an X thrown in. So I have d3p, integral over d3p upon 2 pi the whole cube. Same, the standard original completeness condition, but now with you originally had this p and p, I hit it with a p prime. Now I am going to hit it with position eigenstates. So what I will have there is, let us say, x p y, let us say. This is equal to xy. Now this is still going to be an exponential, because we have seen this earlier on in non-relativistic case. It comes purely from the translation operator or from the fact that xp commutator you want for a particle to be equal to ih cross. So this is going to be an exponential. So you are going to integrate an exponential over this. Okay? So the way we did that last time, it is e to the power I p dot, okay, which one goes? It is p dot, I think x minus 1. Really doesn't matter because it is I could have flipped the sign on this. This is the integral, and that gives you x comma y. Here is where it replaces. If this was not there, and in the non-relativistic theory this was not there, this integral is a nice Dirac-Delta function. Now this is not a Dirac-Delta. What it tells you is that this is not 0 for x not equal to y. I had already seen several signs of this. This is one simple way of saying the same thing. If you take a position eigenvalues of a particle defined in such a way that xp commutator is IH cross, which is the way you would like to have a position and momentum to be defined. We are talking about three-dimensional position and three-dimensional momentum. We are not yet worried about the relationship between energy and momentum, the dispersion relation. That is all which changes between relativity and non-relativistic. If you take the position eigenvalues, you put a particle at y and look for the particle at x, you will find it. That is the problem. In non-relativistic limit, if you put it at x, its overlap at you put it at y, the overlap with x will be Dirac-Delta function. You won't find it anywhere else. Particles can be localized. Here you can. Now it's a good thing for you to do this integral. Now that is fairly trivial because this integral we have done several times in different forms, and you will find that again it is some Bessel function, but it will die down as e to the minus m times modulus of x minus 1. So what it tells you is that this overlap is within one component wavelength. So if you try to locate the particle within that one component wavelength, you will run into trouble. Okay? Now the same result you could have obtained by a different route. Yeah.
So what do you mean by saying that you define the position eigenvalue using the canonical coefficient relation?
If you have, you see, you need to define an eigenvalue, you need an operator. So it is convenient to start with a momentum operator because momentum operator continues to be a good operator in both the cases. So you go to a momentum diagram representation, then the position operator has to be I d phi dp alpha. That is what I mean. Because then you can have a position operator, then that operating on a state will give you standard eigenfunctions, etc. See, what do you do in normal quantum mechanics? Normal quantum mechanics, you think of x as a multiplicative operator and p as minus I d by dx. I could have used position as a multiplicative operator and x as minus I d by dp. I mean, not minus, plus I d by dp. So this is what is more convenient because I start with the momentum operator and do this. I mean, there are various equivalent ways of doing this. All of them will give the same result.
So if this operator is Hermitian, shouldn't it eigenvectors be orthogonal? I mean, why are they not turning out to be?
No, it is not. That is the whole point.
So it's not Hermitian.
Yeah. So the way we are going to, you can define a Hermitian operator by just chucking this away. Suppose I define an operator in such a way that it is actually equal to only this. Right? Or rather, when I take the xp, I take it to be 1 upon square root of 2 omega p e to the ipx rather than just e to the ipx. Then I could have thrown this away. Then I would have violated Lorentz invariance. See, what it tells you is that if you have Lorentz invariance and uncertainty principle together, you cannot have localized set of particles. That is not a surprise at all because uncertainty principle tells you that there is this delta p. I did it in the first lecture. Delta p, delta x, there is an issue. And Lorentz invariance, when a consistent relativistic dynamics will tell you that energy and momentum can be interconverted and particles can be created. So this is just a formal expression of the same result. Okay, fine. Now let us go on to this. Here also I worked out for you exactly the same result. Assume for a minute that the propagator which we have got there, the x2, x1 can be expressed in this form. Okay? Then you take the limit of t going to 0. Then you are going to take the limit of this t going to 0. As I argued the other day, just Lorentz invariant tells you that this is just a function of x square. Translational invariance for a free particle plus Lorentz invariant tells you this is just a function of x square. If it does not vanish outside the light cone, and we found that it does not vanish outside the light cone, I can always make a Lorentz transformation such that the two events are on t is equal to 0 surface. Therefore, I can take t is equal to 0 on that, and this x1, x2 would give me f of minus modulus of x square, that is not 0. It goes as e to the minus omega. So that is consistent with what we have found here. Okay, fine. Now I want to go a little bit into this. The fact that you cannot have this kind of a localized position eigenstates, even though you can have good momentum eigenstates, also tells you that the standard load which we are accustomed to in non-relativistic mechanics, like psi of x, probability interpretation, mod psi square giving you the probability, etc., all of them will fail. Now this is something which you can read in any textbook, but I have not followed that route. You start with something like a Schrodinger equation, then make it Lorentz invariant into a Klein-Gordon equation or some such thing, and then you will show that it does not have a nice probability interpretation. But all of them comes from this, so I don't want to spend too much time on it. Okay. Now let us come back to another issue, which I just mentioned the other day, but which we want to look at in greater detail. I'll probably need this space. When we did the earlier lecture and tried to interpret what this is, I told you that the correct interpretation for this is that you start with a picture where there is a proper time and t and x here. You are taking one event and another event. This event is your x1. It is x2. You are thinking of all the paths which are connecting these two events like this, and all these paths go forward in proper time. At a given proper time, the curve cuts it only at one point. Then I said, if you look at the same thing in space-time, where this is ordinary time and this is ordinary space, the two events are here. You can have paths which go like this, because now this time is just like a special coordinate, there is nothing sacred about it. Therefore, if I take this slice, so to speak, the particle is at 3 different points, which means it has 3 degrees of freedom. If it cuts it 10 times, then it has 10 degrees of freedom. So if I want a causal description of the same system, it should have infinite number of degrees. Okay, this is what we concluded the other day, but we did not know what an infinite dimensional system is, and it will eventually turn out to be a field. But I wanted to do something slightly more non-trivial here, and this is again one of your early exposure to divergent integrals, but it is an interesting divergent integral. This is all fine, but what is really disturbing is a path like this. So let me draw that. T, X. Think of this path. So a particle is just going around in a circle, so to speak. But what does it mean? At this time, there are no particles. At this time, there are no particles. But at this time, there are 2 particles. Right? So we thought of this when we were interpreting this as a particle-antiparticle, even though we have not developed a machinery for that, but something like this should happen. But we already have the machinery to compute this. And I wanted to show that this leads to something truly remarkable. When you compute this quantity in a proper way, it gives you a great insight into what are the things which are going to come later on. So I want to do that computation. So what I want to compute for you is the contribution of energy, contribution to the energy in a particular location or an event made by all these closed loop processes, which we don't even know what it is now. So in order to get a handle on that, we are going to take that contribution. So how do I do that? Okay, we will start using our standard prescriptions which we have. First of all, we have this closed loops And you can think of an amplitude for a particle to end up at a point x after a lapse of proper time mu, starting from the point x with the proper time lapses. This is fine. This is just like it goes around the circle, and the total lapse of proper time along this loop is mu. Okay. Now I want to associate an energy with this. And we know how to do that. If we know something in time domain, then if I do e to the minus I e mu and integrate over all mu, this is something like an energy amplitude. So let me call this B of E x. So this is starting and finishing at some point x, which could be anywhere in that region, and we do know that it is independent of x, so the x is just put in as a notional idea. And this integral over e to the minus I mu tells you that I have translated from a time domain to an energy domain by a Fourier transform. Okay. Next thing I want to do is to add up all the energies, because I want to have a total contribution to the energy. So I am going to do integral 0 to infinity dE of this P E x. Though I am using P, these are amplitudes. In my calligraphy tells you amplitude, I don't take mod squares. So this is what I want to compute. So that is going to be integral 0 to infinity d mu x mu x 0 and integral over dE of integral 0 to infinity dE e to the minus I e mu. Okay, so what is this? Let us try it out. So this integral over dE is going to give me, okay, 0 to infinity here. This integral over dE is going to give me 1 upon minus I mu. I am going to assume that there are I epsilon prescriptions which make the integral converge. So I have this quantity and it is going to be contributed at the lower limit. Therefore, there is an extra minus 1. Okay? So this minus and minus goes away, and then an extra minus appears and I goes on to the top. So it is minus I integral 0 to infinity d mu over mu of x mu x 0. Okay. Actually, I want to take half of this. That is because when I do this computation, I can have an orientation where the path goes like this or path goes like this. I don't want to count both of them, so I will take half of that. So this is, you can think of this as a definition. At this stage, you have no clue what this physically represents. It turns out that it represents something very, very physical, and we will keep dealing with this as we go along into the class. This represents what is known as an effective Lagrangian density. Okay. So with that in mind, I am going to call this L, which is also equivalent to an effective Hamiltonian density minus L. After working it out, I will tell you how this interpretation comes up. We will do that. But right now, these are all just symbols and names. Okay? But this is the quantity we want to concentrate on. It is clear that it has something to do with the total amount of energy which is present per unit volume in space-time. That much is obvious from these integrals. Okay? Except for things like sign, that is what it is giving you. This is giving you an amplitude with an energy E. I have integrated over all energy E, and this is what is lying around because of these virtual loops. So these virtual loops are contributing some amount of energy in this space-time, and we want to know how much it is. For that, we want to compute this quantity. Okay, now there is a trick to compute this. I mean, there are several ways of computing it, but there is a trick to compute this, which let me show you. What you do is you compute the following quantity, dl. You take it derivative with respect to the parameter m square. As I said, this is just a trick. I mean, there are other ways of doing it. So what will it give? Minus I by 2 integral 0 to infinity d mu upon mu. And I want to look at this quantity and the derivative of this with respect to m square. Okay? What is this quantity? This quantity is essentially everything in this on this part. If I do a derivative with respect to m square, I will just bring down a minus I mu times the same quantity. So I am going to write minus I mu times the same quantity, which is x mu x still. The whole trick was to cancel this mu. So this mu goes with this mu. The minus sign and minus sign goes. I into I gives me yet another minus sign. So I get minus half integral over d mu of this quantity. But that is a well-known object. Integral over d mu of this quantity is exactly what I would have called the x to x amplitude. So this can be written as minus half x to x amplitude. This is like x2, x1, this is what we have. Okay? So I want to know what that is. That we know, because this will be equal to minus half. The x to x amplitude you can compute from any of these expressions, and in particular you can compute it from this Fourier transform expression. So if I do that, the x to x amplitude will be just integral over dt upon 2 pi d whole cube, just 1 upon 2 omega p. Right? Because in the Fourier transform, I have put the capital X, the x minus y, that separation, x2 minus x1 vector separation to 0. I could have had a e to the ipx and a omega t and things like that, but all of them goes to 0. So this is what you have. What is this? Left hand side is d by dm square of something. So I would like to write this as d by dm square of some quantity. So this will be, let us look at this as d by dm square of integral d3p upon 2 pi e whole cube half omega p. Suppose I do the derivative. Omega p is square root of p square plus m square. So when I take the derivative of that with respect to m square, I am going to pick up d of omega p upon m square. Is going to give me a half from the square root. Then 1 upon that square root expression, which is omega p. Then omega m square derivative is just 1. So this d omega p upon m square is this half omega p could have been just thought of like this. This extra half goes for a right. So this is minus. That minus is that over. Now I do an integration back and I get the result that L is equal to minus, or rather minus L is equal to, minus L is what I called H, that is equal to integral over d3p upon 2 pi d whole cube. This is a good time to introduce factors, half h cross omega. I think this is a very beautiful relation. And unfortunately, it is not discussed in several textbooks, that's why I spent it on. What have we done? First of all, what is half h cross omega? Everybody knows that. If I had a harmonic oscillator with a frequency of omega, half h cross omega is the ground state angle. If there are harmonic oscillators with different momenta p, if you integrate over all of them, that gives you the total 0-point energy of all the harmonic oscillators. But what harmonic oscillators? We don't have any harmonic oscillator. We had a relativistic particle, single relativistic particle which was going from place to place, right? Then we said it was going from place to place. Then quietly we said that it probably is going from one place to the same place. Then we said that maybe the particle is not even there and here, but it was just a closed loop. Then we computed if such a process can take place, which all came from doing that path integral for a relativistic particle. Now we have taken the particle away. After we have taken the particle away, something remains. What remains is the contribution of energy these closed loops have contributed. And this contribution of energy has an extraordinarily simple and illuminating form as a sum over zero point energies of a whole bunch of harmonic oscillators added. Okay. All that I need to show you is why this minus L is like a Hamiltonian density, which I will do in a minute. Okay. Just believe me on that, because here, except for the minus sign, you know that it is an energy density. Because this is the amplitude for a closed loop process with an energy E, and I have added up all the energies. This is the total energy, and that is equal to this. Much of the computations which we have done, mathematicians will just have a fit, because every integral we have done with this divergent. Okay? But that is not an issue. There is a way of regularizing it by a process called dimensional regularization, which we will do later on. And when you do that, you will get the same result. So that is not a problem. I am not cheating that. And you will find that this is equal to this. But I think you need to actually savor the moment, because this is the first time you are seeing something like a field coming out of just relativistic particles. Okay? And you could not have guessed this result if I had just given you this propagator. You have to be a remarkable genius to look at this propagator and say that the x to x propagation amplitude, if you put x is equal to 0, which is a nicely divergent integral, that divergence is the same as the divergence which comes from here. You have a question? Yeah.
So actually, I think I could follow the math, but I couldn't follow the physics. So
Right.
in the first step, when you wrote the bracket, you are saying that what is the amplitude that is a proper time mu. I start from one space-time point and I come back to the same space-time point. So it's not just the same.
I'm computing the amplitude for this would have been this stuff.
Right. And then you say that. Okay,
Then I say that,
what if
wait, when I am computing this amplitude for this, there is an associated proper time with it. There is a total proper time lapse of the length of the loop in the Euclidean space, which I would have thought. Then I am going to say I don't want to think in terms of proper time, I want to think in terms of the energy in the rest prime of that particle, so to speak. Even though, half the time it will go space-like and all that sort of a thing. So I am going to do a Fourier transform on the proper time. This we have done hundreds of times. So you do a Fourier transform. This I interpret as the amplitude for a closed loop propagation with energy E. Right? So if I have an amplitude for a closed loop to contribute energy E is P of E, the integral over all E would give me the contribution to the energy density by all closed loops. That's what I am computing. Okay? The rest of it is just cosmetics. This half comes in because there are two orientations in which I could have gone down, and I am just taking one of them. Because if it is not a closed loop, it is going from here to here, I can put a direction. But if it is a closed loop, I could have done this closed loop or this closed loop. That takes care of the half. And everything else is just straightforward mathematics. Everything up to this final sign, and that has to do with this being either a Lagrangian or a Hamiltonian. Okay? So is that clear?
And how do you know that it's some kind of density, energy density?
Okay, that is the easiest way is to look at the dimensions. Okay, because this is half x plus omega times d3p. d3p is like 1 upon L cube. That's the easiest way to think about that. It's the energy density. But if you do it properly with all h crosses and c's thrown up, it will turn out to be a density. Okay, fine. Now let me spend a little bit of time. Okay, I have just some yeah.
We usually do it with probabilities, not probability densities. So
No, I am doing everything with probability amplitudes.
yes, in statistics,
Yes.
what we do is we do it with probabilities. Not
What do we do with probability?
Means in calculating the mean values or.
Oh yeah, sure. But there is a difference between quantum mechanics and statistical mechanics. In statistical mechanics, you use probabilities. In quantum mechanics, when two slits are open, the amount of electrons you find at one place is less than with one slit open. You will never get it with probabilities. So you need something to kill what was contributed. Therefore, you need interference. So you need positive and negative quantities. Probabilities are always positive, good probabilities. So you have a amplitude and you have to add the amplitude. So since we are doing it quantum mechanically, we have to work with amplitude. These are not processes which you can look at and collapse to some eigenket or something. Okay, so that is a fundamental requirement. That has nothing to do with vacuum or anything. All these things which I am writing down are amplitudes. Like that x2, x1 is not a probability, it's an amplitude. If you take mode square, you will get nonsense. Okay, fine. So, let me, since I have 10 minutes, okay, I have two things to do, so I'll try to do both of them. Let me finish off one simple thing first. All these conclusions which we have obtained, the main pillar on which it is standing is this expression. Right? This original expression from which we concluded all that. Okay. Now this expression I derived using the Jacobi identity. And not Jacobi identity, the Jacobi action, sum over the Jacobi action. Jacobi has done too many things. Okay, so as a result of it, we found this expression. At that time, I told you that there is a much more rigorous way of deriving the same expression. This has been given in the handouts last week, which I think you should mandatorily read. And the rigorous way of doing this is again in the Euclidean sector. What you do is the following. You attribute e to the minus m times the length of the path between two events x2 and x1 with every path you choose. Then you sum over all paths which connect two events. This is what you are doing in the Euclidean sector. There is no I here. Okay? Now in the Euclidean sector, I can put a Euclidean lattice. So you have a lattice placing epsilon. Therefore, the length x2, x1 will become this entire sum will become the number of paths of some particular length L connecting from origin to a lattice event. Or rather, you are taking a vector which has integer coefficients on a lattice, which finally will translate in the space-time to an event. This is the number of paths of length L connecting these two. You multiply it by this e to the minus m times that length of the path. And you sum over all of them. So all that you need to compute is what is the number of paths which take from origin to a particular point of length L. That is a combinatorics problem which was given as an exercise in the first week. Using that, you can compute this on a lattice with a lattice spacing epsilon. In order to give meaning to the path integral, just like you do time slicing and then take a limit of epsilon to 0, I have to define how I go from lattice to the continuum. There are two regularizations which are required. One is that you know that this mass has dimensions of inverse length. So if you are doing it in a lattice, it will essentially go as 1 upon epsilon, where epsilon is the lattice spacing. So you replace this mass by some mu of epsilon, and you choose your mu of epsilon so that things converge. Then you put in an overall measure, they call some m of epsilon. So given that m of epsilon and mu of epsilon is a proper choice, you can define this path integral on the lattice, and then you can work everything out. If you do that, you will end up getting that Euclidean momentum representation for the propagator, which I wrote down, e to the ip dot x upon t square plus m square on the lattice. The Fourier transform of that will give you this. So there is a rigorous justification for this kind of an object, and that is what we have been using for everything else. So it is important because since everything is tied to this, it is important to know that there is a rigorous way of deriving it. The Jacobi action is intuitively very good, but it is not rigorous because I didn't define the measure, etc. Here you will be defining the measure and all that kind of quantity. Okay? Now the second thing which I wanted to do was, why is this an effective Lagrangian? Now the concept of an effective Lagrangian and all the details we will be doing in full glory when we do field theory. But I just want to give you an intuitive feel for that. Let us go back to the very first lecture or whatever, where we did this sum over path. Now let us take quantum mechanics again. There is an x of t we said even quadratic will do. Exponential I time, there was an action which depended on this path x of t. Then we said let us write it down as e to the I times a classical, because it was quadratic we could separate it out, and then summation over the fluctuations around the classical path, which we denoted by q, and then wrote it as exponential I a of q. I hope you remember this. Okay, we discussed at that time that if it is quadratic action, then when you separate it out, there is one term with a of fc, one term with a of q, there is a linear term whose coefficient will vanish. Therefore, these are the only things which is there. Then we did this computation and we wrote the answer for quadratic actions for a closed system again as n of t e to the I a of the classical path. Right? So you started with something and you summed it up. Now let us go back to your Statman analogy. See, in Statman we do something very similar. We do a sum over n of e to the minus beta en. Right? It's almost like that sum which we have written down there, except for I factors and things like that. But when you do that, you can call it partition function and you can work completely with it. But you find in Statman that if you write it as e to the minus beta times some other quantity, which is called free energy, then things look much nicer in terms of that. Something similar happens here. You could have written it as n of t times this, but you can also write this as e to the I time an effective action. Okay? It already has an I times classical action. What remains here, this n of t, you are writing as some correction. And most of the time it is convenient to separate out this classical action, so you write it like this. This effective action comes entirely from quantum mechanics. That is this n of t. Okay. Now, what do you get when you compute n of t? This n of t comes from quantum fluctuations. Once again, there was one exercise where I had asked you to compute this for a matrix kind of a situation. What you are computing in the quadratic case is an integral of the following form. So this n of t comes from, so n of t is e to the I times a effective. This is what we called n of t. This comes from sum over q of t of a quadratic expression which is exponential I. Since it is a quadratic expression, I can write this as dt some q of t, some operator d, another q of t. I hope you are with me up to this point. So this is what you would have computed. Now the exercise which I gave you, if you have done, you will find that this is proportional to determinant of that operator to the minus half. Good. Those of you who have taken Professor Gangel's course in path integrals would know this because you can diagonalize this and you can write it like this. So you get determinant to the minus half. I want to get it into an exponential form. So what is determinant d to the minus half? Determinant d to the minus half is exponential log of the same thing. Log is minus half, log of this, log determinant of d. Right? There is a formula which tells you that log determinant of d is trace log d. I don't know whether all of you are aware of this. See, if I have a determinant, think of the matrix as having been diagonalized by a similarity transformation, then determinant will go as the product of eigenvalues. right? So what we are computing there is log of determinant of t. So if I do the log of this, I have to take a log of this. Log of a product is sum over log of lambda I. Log of lambda I is what is thought of as the eigenvalues of our matrix, which is log D, defined by Taylor series expansion suitably. So there is a log of D here, and you are summing over all the eigenvalues, which is like taking the trace of it. So in case you did not know that, you should work that out, or I will throw it in this time as an exercise. So this is exponential minus half trace log D. We are almost there. Don't lose heart. So this is trace log D. Now you just have to define this trace and this in a suitable manner. Okay? The way we will do this is that, so we can this is determinant of to the minus half. So this is your exponential I as effective, right? So if I write an I and an I here, put an I here, and an I here, this is what my effective action is going to be. In things like constants, etc., we won't worry about right now, but it has to be a trace log D. Okay? I by 2 times trace log D. Now suppose I have an operator and you have a set of eigengets for that operator. Then the trace operation is an integration over the eigenvalues on that eigenget. Now you go back and see what we have here. You see everything here except a log. So where is the log hiding? The log is hiding because log has an integral representation, which I have used there. So let me work that out, and then we are done. There is a formula which tells you that integral 0 to infinity du upon mu of e to the minus I mu d is minus log d. The way to prove this formula is to differentiate both sides with respect to t. Then you will get a minus 1 by d here, and that integral will give you minus 1 by d. Now the formula as it stands is meaningless because the integral on the left hand side is divergent. Near mu is equal to 0, this will give you 1 and it will level again. But that doesn't matter. The reason is that if you have some log d by some log d naught, which you will always have because there are proportionality constants going on here, you can think of it as this minus something else, and that will take care of it at that mild divergence at mu is equal to 0. So you can use this. This is precisely the structure which we have got. Just to remind you, this has yet another expression which we wrote down in one of the previous lectures as x e to the minus I mu box plus m square x. You remember that? So there was a e to the minus I mu times an operator with a d mu over mu sitting here. This is nothing but a logarithm of this. That logarithm sandwiched between x and x, if I had integrated, would have given me the trace. Okay? So this trace interprets. So at this case, what you do is you write this as exponential I. Then what remains? You write it as I by 2. Since it is 4 dimension, you think of the trace as d4x, sum x, log d, sum x. Okay? Then, since we want this A effective here to be some kind of a Lagrangian density, but actions are integral over dt of a Lagrangian. But if Lagrangian has a spatial density, there is another d3x there. So this is what I am going to think of. This I by 2 times this is what I am going to think of as the Lagrangian density. So the Lagrangian density which we wrote down somewhere here, this, okay, is this d mu over mu integration which is going to come from translating this log d. So let me write it down explicitly. The Lagrangian density which I am going to think of is I by 2 times everything here, that is 0 to infinity d mu over mu of x e to the minus I mu t. This is exactly what I have got here. So this is the whole idea of thinking of this as a Lagrangian density or a Hamiltonian density. Now, much of this would not make sense for you right now. Don't panic, because we are going to do this effective Lagrangian in great detail later on. But this was only to tell you that this L which I introduced here has a meaning. And all that you need to remember at this stage is the following. First, this comes from fluctuations. This e to the I effective came from doing the fluctuation. Here the fluctuations are things from the closed loops. So you are doing some kind of a fluctuation, some kind of a virtual process. We are doing that. And then what you have here is an energy density, because minus of Lagrangian is a Hamiltonian. That energy density can be expressed as a half h cross omega c, which is the surprise of the day, so to speak. That this tells you that somewhere deep inside, this relativistic particle knows about a whole bunch of harmonic oscillators. Each harmonic oscillator having an frequency omega k, and that omega k is related to k by square root of k square plus epsilon. That is what we will cash on and work further in the next lecture. Okay, sorry for overshooting a little bit. Questions? Yeah.
So, this is concerning the when you were calculating the propagator.
Right.
So, depending upon what boundary conditions you have, like
Yes.
it will come out to retarded or.
That's correct.
Right. So, in case of final propagator, what are the boundary conditions? Like, so for example.
No, the boundary condition was how you leave out the. Okay, there are two ways of talking about boundary condition. One is if you have an integral and the integral is ill-defined, and if I tell you the correct prescription for avoiding the poles, that is equivalent to a boundary condition. Then once you have evaluated the answer, you have a clearer idea as to what boundary condition you have put. In the Feynman propagator case, the boundary condition is take the positive frequency modes, propagate it forward, take the negative frequency modes, propagate it forward. That is the boundary condition. So if I have a harmonic oscillator and you think of, this was what the exercise was, d square by dt square plus omega square times some g of t is equal to delta of t, and you want to look at what the Green function is. When you work it out, you will find that the integral is ill-defined. You can either say that any source should disturb or produce an effect only later time, that will give you a retarded propagator. If you say it is advanced, then you will get an advanced propagator. You take the source, decompose the source into positive and negative frequency modes, propagate all the negative frequency modes backwards and positive frequency modes forward. That would give you the Feynman. Any other question? Yeah.
I understood why it is called L, the Lagrangian density,
Yes.
but why is L minus H?
Oh, because any Lagrangian density, if there are no derivatives etc., is equivalent to minus the Hamiltonian density. P q dot minus L. And the P q dot is not contributing here.
Is there a physical significance to that? There is no
Yeah, actually there is a proof that if you add a small perturbation to the action, and if you add a small delta perturbation to the Lagrangian, then the corresponding perturbation to the Hamiltonian is minus delta. So, for example, Landau has the proof of this. It's a very general research.
So,
Yeah.
here the expression for the energy,
Yes.
omega p is like different spin constants.
Omega p is like?
Spin different.
Okay. So you are thinking of oscillators as springs or something. Usually. Okay. Oscillators are things which are decided by a dispersion relation. See, this expression which I have derived is what a condensed filter set for phonons or for any other phonons. Okay. So magnons, whatever you have, for every one of them, he will attribute a wave vector k and an associated frequency omega, and the entire condensed community would like to know the dispersion relation for a particular excitation. What is the relationship between omega and the momentum? In relativity, relativistic invariance gives it you very trivially. as square root of p square plus m square. That is what we are using. So you should think of it as analog of energy and momentum associated with an excitation rather than as a spring constant of the harmonic oscillator.
And these are all the ground states. This,
Okay. Yes, this half h cross omega is the ground state energy because none of the oscillators has been excited. But what is interesting is that if every oscillator has half h cross omega and there are infinite number of them, when you add them up, you get this much of energy.
the main expression is initially there is no particle.
Exactly, that picture which we drew, there was no particle in the beginning and no particle in the end, so to speak. I mean, you define some end and beginning. Then in between you have loops, and these loops are going to contribute for you this much of energy.
So if I draw a line like this, a single particle, will like this, and then some sort of closed loop.
Sure, you can do that. Yeah, that is a good question. So you can have processes like this. Right? So you can think of it as a process in which there is a particle which went from here to here. And it just so happened that an antiparticle-particle pair was produced and it just touched it at this event and went around. So what happens is that these kind of things can be just removed, so to speak, and studied separately.
So at that time, when energy contribution I will get, will it be the ground state energy?
The energy contribution of this closed loop all integrated together is only going to be the ground state energy. Right?
If I make calculate from the first, you make it mu1. Okay, 0 to mu. And in between there is a loop.
Yes.
So I don't care at what time this loop was there.
Right.
So if I integrate that one, suppose 0 to infinity, the particle can move from.
No, but you have to also calculate all the loops. I mean, you shouldn't stop at one loop. I mean, there is also another loop here. Right?
That I am taking care by taking mu goes from 0 to infinity.
No, you can't take care of that. Because the 0 to infinity is only going to give you this with different energies. See, you put e to the minus I e mu and integrate over mu. That only gives the amplitude that this loop had a different energy. It does not take into account another loop, so to speak. So you have two integrals here. One integral over mu and another integral over e.
So that takes care of all the.
Exactly. And you have to do it in that way in order to get that correct d mu upon mu. See, the nice thing is, if you do it like this, you get an I by 2. There is a factored half. That gets an interpretation in terms of the loop's orientation. Okay? And that half is crucial because when you do the integral, you get determinant d to the minus half. You can't do away with that half. Okay? And then the logarithm comes in. Logarithm has a d mu upon mu. That 1 by mu comes because you first wrote down the amplitude for this P and then you integrated over all this dE, that is what produced that 1 by mu. So everything has tied in very nicely to give you that result. Any other comments?
One question related to that diagram that you
Yeah.
I mean, the way you drawing.
Yeah, that diagram is a little bit schematic, but anyway, go on.
So basically, initially started with the one particle.
Yes.
Over in time.
Right.
Now the second circle that you do, it seems like there are at that particular time slice there
Yes.
is 3 particles.
Yes.
So this is such a.
Yes. So what we are talking about is there are two ways of thinking about this entire phenomena. One is, I mean, loosely speaking, what I would have called a Schwinger approach, where you take one particle and you let it propagate in proper time and you let it do whatever you want. And that will ultimately get you the same result. But when you are doing this, you don't get causal propagation in your space-time. You cannot have a system which is propagating causally in the space-time from t is equal to t1 to t is equal to t1 plus epsilon plus 2 epsilon, etc. If you want that, then you need to have something which has infinite number of degrees of freedom. You start from here, you go here, you go here. The number of degrees of freedom will keep changing as to where you draw this line, which is what fields do. So the field dynamics will take care of it.
So even initially you don't start with a single particle. Initially
Yeah, but we don't even know how to define a single particle. Because a single particle at this location we have shown is ill-defined in the field theoretic context, right? Because there is no nice position eigenvalues. In fact, that is the thing which you should look at in standard textbooks. If you take any standard quantum field theory textbooks, unless it's a very old one like Schwaber, they will never talk in terms of position eigenvalues. Because they don't exist. I mean, they don't exist naturally in the field theoretic context. The closest to it is what Gaurav asked some other time, which we will come back to, that phi of x acting on the vacuum, whether it can be interpreted as a particle at a point x. But there are ifs and buts about that interpretation. Any other comment? Okay, so let's read tomorrow. You didn't get bored to hell.